But now let's consider what is going on inside the box. Inside the box, the potential is zero, and so we have the same set of conditions as we had for the free particle. V is zero, and therefore the wave function inside the box is satisfied by the same term as we had for the free particle, ae to the ikx plus be to the minus ikx. Or we can write that as c times cosine of kx plus d times the sine of kx. Now, it may well be that c and d are complex terms. I've got to absorb an I term in there somewhere. So c and d may well be complex. But let's just see what happens. Well, if we have an infinite box, that is to say, the potential is infinitely high, then we know that outside the box, the wave function falls to zero immediately. And that means that the value of the wave function at the two ends of the box is zero. So whatever the wave function is doing inside the box, at the two ends, it must be zero. So we know that psi at the point x equals 0 equals c cosine of kx plus d sine of kx. But when x is 0, this whole term is 0. And when x is 0, this whole term is 1 multiplied by c. So when x is 0, psi of 0 equals c. But we know that at x equals 0, psi of 0 must be equal to 0. And therefore c must be 0, which means that term disappears. It can't exist. What about when x equals L, that is at this point here? Well, then at x equals L, psi of L equals, well, there's no term here because c is 0, so it's simply d sine k L. And that is satisfied when kl equals any multiple of pi, because psi L also has to be 0. That means that k equals n pi divided by L, and that means that there are only allowed levels of the wave function. Psi equals d sine n pi over L times x. And that is the value of the wave function inside the box. Now what happens if n is 1? Then we get this function. What happens when n is 2? We get this function. When n is 3, we get that function. The condition is that the wave function must be 0 when x equals 0 and when x equals L. In other words, at the two ends of the boxes. What about energy? Well, energy is p squared over 2m, which equals k squared h bar squared over 2m. But we know what k is. It's n pi over L. And so the energy term becomes h bar squared over 2m times k squared, which is n squared pi squared over L squared. And that means that energy again is quantized in these units. N is an integer, and therefore there are only certain allowed energy levels. But we said that the value of the wave function inside the box, which has infinitely steep sides, is psi equals d sine n pi over L times x. What is the value of d? That is what we now need to go on to discover. Well, we want the usual requirement that the absolute value of psi squared, which is the probability of finding the particle, is 1 when you integrate it over the whole of the length of L. So what we need to do is to integrate from 0 to L of the wave function squared. So we're going to square this wave function, and we get d squared times sine squared n pi over Lx dx, and we require that that equals 1. Now, the integral of a sine squared term has an average of 1/2. So psi squared is the integral from 0 to L of 1/2, which is the sine squared term, times d squared dx, and that must equal 1. And that equals d squared over 2x evaluated from 0 to L, which is d squared L divided by 2. And that must equal 1. Consequently, d squared equals 2 over L, and d is the square root of 2 over L. And so we come to the wave function of the particle in a box with infinite sides, that psi equals d, which we now know is square root of 2 over L, times the sine of n pi x over L for a particle in a box of infinite sides.